Everyone, my name is Harini. I'm a research fellow at RMIT University. And today I'd like to give you a very quick overview on some of our recent theoretical work in this field we like to call nitrogen vacancy plasmonics, which is about plasmonically controlling diamond quantum devices, particularly ones using plasmonic NV centers. Sensing magnetic fields at very small length scales is becoming quite important across many fields, as I'm sure most of you are aware. And this ranges from things like sensing activity inside cells, all the way to miniaturizing different kinds of devices like the read-write heads of our hard drives. And the possibility or the idea of using a single quantum emitter as a magnetic sensor was first proposed by two gentlemen named Chernobyl and Berman back in 2005. And this, what you see here, is a schematic of their seminal proposal. And the idea was that if you're just using a single quantum sensor that's either atomically small or nanoscale as a sensor, it could go extremely close to your samples and do very high resolution scans and measurements. And it could even detect other single spins that are comparable to the size of the sensor. And optically detected magnetic resonance, or ODMR in short, is one of the most popular techniques used to measure magnetic fields by sensors like the ones proposed by Chernobyl and Berman. And this technique is particularly used to sense static magnetic fields. And what you see here is an abstraction of a certain class of quantum emitters that can be used to perform ODMR. So let's have a quick look at how ODMR would work. Let's say our sensor has an orbital ground state G and an orbital excited state E. And let's say both of these are spin triplets, so they have three different possibilities of angular momentum, intrinsic angular momentum. And we can drive spin preserving transitions between these ground states and the excited state using the appropriate kind of laser. And once excited, let's say the system can come back down while preserving the spin and giving out a photon. And there's also usually other pathways for spin to come back down. Let's say there's an intersystem crossing pathway or a non-radiative decay happening from the spin excited plus or minus 1 states of the upper spin state, upper orbital state to the ground state. Which means if we send our system from the spin 0 in the ground state, it's more likely to come back down giving out photons. And if we send it up from the spin plus or minus 1 states, it's a bit more likely to come back down without giving out photons. So when the system looks a tad bit brighter when it's in the spin 0 state compared to the spin plus or minus 1 states. Right. So with that bit in mind, let's have a quick look at the spin subsystem at the bottom. So let's say, for the argument's sake for the moment, that these plus or minus 1 spin states are degenerate, and we can drive spin preserving spin transitions between the dark states and the bright states using a microwave field of the appropriate frequency. So when the microwave frequency matches the energy gap between the states, the bright and the dark spin states, you'll see a steep drop in fluorescence. And now, if these states are responsive to static magnetic fields, let's say they split apart, for example, if you when you apply a static magnetic field, you'll see multiple dips. For example, in this case, 2 dips, and the gap between these dips would be proportional to the static magnetic field that you send. So all you have to do if you want to sense a static magnetic field with a sensor like this one is to go place it wherever you want to sense the static magnetic field at, shine a laser, and then scan a microwave field, and then measure the gap between the dips and translate that using a simple conversion factor to the static magnetic field that you were trying to find. So that's a very quick crash course on ODMR using a simple abstraction, perhaps an overly simplified one. The nitrogen vacancy center in diamond is an excellent system that can be used to perform this kind of sensing procedure. Here's a cartoon representation of the NV center. It's a defect in diamond. It has a vacancy or a missing carbon atom next to an impurity nitrogen atom in the diamond lattice. And thanks to these NV centers, several breakthrough quantum technologies that can even operate at room temperature are already getting here. These include things like quantum computers that can operate at room temperature without having to live inside refrigerators, and single spin-based quantum magnetometers that can go very close to the samples and do high-resolution scans and measurements, like Chernobyl and Berman proposed in 2005. And these kinds of devices are even commercially available by companies like Quantum Brilliance, QNAMI, and QSaber, which you can look up later if you're interested. And there are even lasers that can be controlled using tiny changes in magnetic fields that are under experimentation at the moment. So this list goes on. These are just a few different examples of amazing quantum technologies based on NV centers that are coming out. And we're looking at the possibility of enhancing these kinds of technologies using plasmonic particles in NV plasmonics, at least theoretically for the moment. And what you see here is the quantum optical abstraction of the NV center that we use for our NV plasmonic computations. Now, as you can see, it's a tad bit more complicated than the very simple abstraction we used to discuss ODMR, but as you'll see soon, it's operationally very similar. So let's have a quick look at what's captured in this. So as usual, if you shine a laser that's of appropriate frequency, it will drive transitions from one of the ground states, so these are vibronic states in the ground state, to the excited states, to one of the vibronic states in the excited orbital state. And once in the excited state, it will quickly rattle back down to the lowest energy excited state, where it is relatively the most stable in the excited, when excited. And from there, it can come back down, giving out a photon. And if there's any excess energy, that will dissipate in vibronic transitions. And if you recall from the ODMR discussion, there will be a non-radiative decay that does not give out photons happening from the spin plus or minus 1 states. And each of these blue bands are vibronic levels, and each of them is modeled as a spin triplet that can undergo the microwave and the static magnetic transitions that we discussed at the start. So that's a very quick overview of our NV model. And now if we keep a plasmonic particle, like a tiny gold or a silver particle next to our NV center, it can help us to greatly enhance or suppress the amount of photons coming out from the NV center by changing the photons taken in by the NV center. So these optical signals, the excitation and the emission signals, the optical ones can be engineered using by appropriately placing a plasmonic particle. And these are the readout signals of the spin, magnetically controlled spin phenomena that are going on inside the NV center. So that's what we're trying to do in NV plasmonics. Just to give you a quick overview of how this interaction is modeled, I'm not going to go into all the details of the math in this very short presentation. You can find all that in our recent paper here, but I'm just going to go through the very basic steps to give you an idea. So we first write down the Hamiltonian or the energy operator, looking at the NV center as a quantum system and the plasmonic particle as a classical particle that modifies the optical field and therefore the Rabi frequencies of the NV center. And then we look at how the NV center state evolves in time while interacting with the environment. And in this stage, we take into account how the plasmonic particle modifies these environmental interactions. In particular, how fast the NV center decays. And once we have solved this master equation, we take a Lindblad formalism to do that. We can do a lot of things, like we can compute the optical photoluminescence spectra, we can do different time domain analysis, or we can microwave frequency sweep the steady state answers and get things like ODMR spectra, for example. So after developing the model, we verified that it works as expected by comparing its predictions against several experimental measurements in the literature, both in the absence and the presence of plasmonic particles, and apparently the model satisfactorily mimics the variations as expected. So after the derivations and verifications, we wanted to look at how plasmonic interactions could enhance the spin readout or magnetically controlled phenomena of NV centers. So here's a quick snapshot of what we've done. What you see on the top left is, if you remember from the first few slides, the typical line shape we measure when using the NV center for static magnetometry. This gap between the dips is proportional to the static magnetic field that we're trying to measure. And the larger this step D and the brightness we get, the easier it is for our signal to stand out from noise. And what you see here is a typical spin qubit readout signal that we would measure if we are using the NV center as a spin qubit and when we want to read out its state. This top solid line shape is what we would get if our NV center is in the spin 0 state when we start the measurement procedure. And this dash line shape at the bottom is what we would get if it starts off in the spin ±1 states, which we will typically assign as the bottom of the qubit or the Bloch sphere. And this area in between is called the contrast that helps us to distinguish between these extreme readings. And model predicts that if you carefully place a plasmonic particle next to an NV center and appropriately tune the permittivity of the outside medium to get the plasmonic resonances to align as needed, we can even get several fold or orders of magnitude enhancements of these things like the brightnesses, depths, and the contrasts in certain parameter regions. But these do not occur everywhere. It takes a lot of careful tuning, apparently, and that's where we hope that theoretical modeling could go hand in hand with the experiments to give an idea of where to look for these enhancements. So that's a very quick overview of what we've done so far. So our theory can currently help to enhance the NV centers as qubits and magnetometers. And we're looking into expanding further into how these capabilities could be enhanced with plasmonics, because we've only touched upon a few things at the moment. And we also aim to gradually extend these to capture possibly a lot of or all the capabilities of the NV center, ranging from electric sensing all the way to nuclear qubits in diamond. And we hope that plasmonic engineering could help to enhance many NV-based quantum technologies, some of which are even being commercialized at the moment. And these could range from things like sensing activity inside cells all the way to controlling quantum computers or the building blocks of quantum computers at room temperature. So with that, I'd like to finish this quick presentation. I'd like to thank my co-authors of the work I presented, Professor Jared, Francesco, and Professor Federico. And I'd like to thank our funders, RMIT and Extend Science. And thank you all very much for your kind attention.
Thank you very much, Harini, for your interesting presentation. We can take one or two questions, please. The session is open for the discussion. I have a small question. In a slide, you showed that there is radius versus contrast and brightness in the previous slide. Yeah. So here it's looks like very interesting. If you are changing the radius, then there is change in the brightness and we are getting a maximum value. So I am interested to know the reason behind it, why it's happening so.
The radius changes things like the plasmonic resonance, and these enhancements are actually not happening because of a single reason. For example, if you look at how this diagram is, there are certain like it is a rest fields, and so we have to strike a perfect balance between the things, for example, to reach a maximum. Does that answer your question?
Yeah, okay.
I have, oh, sorry, can I?
Yeah, we have 50 seconds. Please go ahead.
Thanks, Harini, for the nice talk. I don't know if I really understood. It's a theory work, huh? So
yes.
I don't know if I understood correctly. How do you go, like, how are you going to implement this plasmonic nanoparticle in your diamond NV center? It's like how are you going to attach that option to enhance the performance of your NV center? It's like some kind of, you want to dope into that together with the diamond, or how do you think that is going to work?
So in this case study, we haven't actually looked much into the aspects of experimental implementation, but there has been studies that have controlled the interaction between the two, for example, by placing a diamond on a microscope, benchtop microscope, where an atomic force microscope is attached on the top, and they carefully use that tip to place, like push over a gold nanoparticle close by.
I see.
Yeah, that's one of the experiments that I've seen, and there are also ways to attach nanodiamonds to plasmonic particles colloidally. I'm not very aware of the experimental details of how they attach it, but there has been studies where they try to make colloidal solutions of these kinds of dimers and co-satellite kind of structures.
Okay, I think our time is up,
Okay,
so
yeah.
maybe let's. Thank you. Yeah.
Thank you very much once again.
Yeah.